Well, Mr. Sams.
Why are you wearing your safety glasses? We're sitting at a desk.
Because last time when we did experiments,
Yeah.
you did not wear your safety glasses.
Right, but we're at a desk.
Yeah, but we're going to do experiments. We're scientists, and you're not wearing your safety glasses. What's up with that?
Well, I'm at a desk.
But I'm prepared.
Oh, I see.
I am prepared for the experiment
You don't
we're
want to look
doing.
like a fool like I did last time without
Yes,
having mine
he
on.
was being the fool he was not supposed to be. Mm-hmm. So today, the last section, electrolysis and little practice problems here.
Yeah.
So let's kind of go on this. Electrolysis. Okay. We've been learning about galvanic cells that are batteries.
Yes.
But there's something that's opposite.
Yeah.
They're called the electrolytic cells.
Yep.
But in this case, we're going to pump electricity through a non-what?
Spontaneous. Because with our galvanic cells, you hook them up and they go because there's the spontaneous reaction.
These ones don't go. You can only make them go if you add things together.
Yeah, and they're just the reverse of the spontaneous reactions that normally go.
Right.
You just shove
so
electricity.
Let's do a compare and contrast. The first picture is the picture of a galvanic cell.
Yep.
Well, cell. So that's the galvanic cell, and notice that here the voltage here is a positive 1 volts. And if we go over here, we have a different reaction. They have a power source right here, and they're adding 1 volts, and it drives the electrons in the opposite direction. This is actually the basis of a rechargeable battery.
Mm-hmm.
Is that you can get the batteries to work in opposite directions. So when you take your cell phone with its rechargeable battery and you plug it in, you are causing the reaction to go in the opposite direction.
Yes.
So it's very cool how all this works. All right? All right. Before we do this, let's kind of define some terms. Now, an electrolytic cell, what is the definition of an electrolytic cell? This is where you use electricity to what?
Produce a chemical change.
Produce, P-R-O-D-U-C-E, a chemical change.
Now that's the opposite of a galvanic cell, because in the galvanic cell we have a chemical change used to produce electricity.
That's right. And electrolysis particularly is what? Now that's a little bit kind of a special case.
That's what we're just talking about, where you force the current through the cell to make that happen.
So force the current to produce. How's that different
Than
electrolytic cell?
Well, the electrolysis is the process we use to make the electrolytic cell work.
Yeah, so this is really the process, and the electrolytic cell is a device that makes it work. Okay.
Yeah.
Now, when we do this, we also measure a particular unit we haven't talked about, and that is amp, or an ampere, named after some guy named Mr. Amp, I think. And an amp measures essentially the current flow. It's also called the current. Now, where have you heard current before?
In the ocean.
Yeah, there's ocean currents, or maybe possibly like if there's a river flowing, you can measure how fast the river flows.
That place in Colorado Springs that sells greeting cards and checks.
No.
No, different?
I think that's something different. You're all silly, Mr. Sammys. All right. So a current is actually how fast the electrons flow. So we measure that in something called a coulomb per second. A coulomb per second is an amp. So if you have 1 coulomb per second, then it's 1 amp, or 5 coulombs per second, 5 amps, etc. Now, a Faraday, we learned about this last time, but you'll see it's kind of important in this particular unit, or this podcast. There's 96,485 coulombs for every 1 mole of electrons. We'll need this when we do the math here in a little bit. Now, electrolysis, this is pretty cool. This is a picture of electrolysis. There's a battery right here, and we can, Mr. Sams? I wonder if we could do this.
Let's hook it up and see what happens.
Yeah. All right, folks, what we got going on here is I have a beaker, and in that beaker I have 2 test tubes filled with water. Now, one thing I did do is I made sure that I added some salt to the water, because it won't work because water doesn't conduct electricity. However, the salt does. Okay, and then I have it connected. There's a wire. If you look way down in here where my fingers are, it's kind of got some bubbles in it, but you can see a wire onto both sides. These are my anode and my cathode. This actually doesn't require 2 separate cells, but I think it's cool if you have 2 separate cells. And then over here, I have a power supply. It says AC/DC power supply, and
like the band.
Like the band. And so if I turn this on, okay. So what should be happening right now is that we should be getting power coming through our system, and I'm not seeing why it's not working. Oh, there we go. So everybody, if you look, I forgot I put the wrong power. If you look on this particular cell, you'll see a gas being given off. You see the bubbles, and they're rising to the top. And on this side, you should also see the gas given off, but it looks like it's harder to see it. It's going at about, I can see it. Maybe if we turn this around, we can see it. Yeah. All right. Mr. Bergman will see if he can get the bubbles are in the way.
By the way, don't stick your finger in that water right now.
I don't think that would be a good idea.
No.
All right, I can see the bubbles right here where my finger is pointing, and this is
definitely.
producing a gas. And if you zoom into the top, you'll notice that we're producing a gas right here. Now, this one is producing at twice the rate as this. Since this is water, this is separating water. This is the electrolysis of water.
All right, electrolysis just means splitting by electricity.
And so I am producing hydrogen in this particular tube and oxygen in this tube. And the reason I know that is because this is being produced at twice the rate of this one. And so in H2O, you'll make twice as much hydrogen as you will oxygen. So this is the electrolysis of water. You could do this with lots of other things, and we'll talk about that in just a moment when we go back to our podcast. So, let's see. So you can see, here's a picture. The picture probably, we saw it live in action, but if you look at this picture, this would be the hydrogen side right here. Might probably need a darker pen, I think. This would be the hydrogen side, and this would be the oxygen side. So we got to see it live instead of just a boring picture. Okay, let me tell you a little story.
Tell us the story, Mr.
Actually, before
Bergman.
we do the story, let me tell you about my interesting story about electrolysis. So I'm in college. And
Stick your finger in?
No.
Oh. That'd be
I'm in
pretty
college,
interesting.
and I get this field trip to this place, and what they do is they're plating chrome, a chrome plating factory.
Like
You've heard of-
bumpers and stuff?
Like bumpers and stuff.
Oh.
And the number of amps that they would run through this thing was like 100,000 amps. So they had this big cell.
By the way, if you get electrocuted, it's not the volts that kill you, it's the amps.
Yeah. And so there was this huge thing that was the size of a car, this big buck, filled with potassium dichromate. By the way, that's a very nasty chemical.
Yeah, dichromate's icky. So it's orange.
So it was orange.
That's an AP question, by the way. What color is dichromate?
It's orange! And then they would stick into their device, and they would have it hooked up to some metals, and the dichromate would plate onto chromium. And it was like 100,000 volts. I mean, if you touch that solution, dead. You die.
Volts or amps?
100,000 amps. Yeah, it was...
Wow.
This was the biggest electricity user in the county, I guess. These guys. And then, of course, I found out later on that these guys got put on the Superfund site.
Ooh.
You see, because they had this
That
thing
means
called...
big toxic mess.
Because this dichromate, even though it chrome-plated things and it made it pretty, and you could chrome-plate things like milk things, and it made it very safe, the extra dichromate got like thrown into their backyard, so to speak. And then the EPA got involved and found out that they were dumping in the backyard, and
Oops.
the company went out of business.
Gee, you think?
Yeah, bad news. So it was very cool to go there. However, I didn't know they were doing unsafe practices and polluting the world. So anyways, side note. Another interesting story. Aluminum. This is a guy named Charles Martin
It's like
Hall.
he's about 16.
And actually, he was about 16 when he did this. And the price of aluminum in 1855,
$100,000 a pound.
$100,000 per pound.
By the way, another side note. I don't know if you're going to talk about this. The top of the Washington Monument in Washington D.C. They put an aluminum cap on it because they finished building it in the 1800s, shortly after the Civil War. They put an aluminum cap on it, basically to signify, hey, we've got this really expensive metal. We got money to burn because we're an up-and-coming country. We're going to cap the Washington Monument with aluminum.
Whoa!
Yeah.
That's because it costs $100,000 a pound.
Exactly.
Well, it turns out
Now it's like, oh.
there's this dude, Charles Martin Hall, this guy right here, and he
We'll
was
call him Chuck.
He was a Chucky, and he was a student at Oberlin College. And basically his professor said, if you can figure out how to get aluminum and make it cheap, because aluminum oxide, Al2O3, is very, very present all over the world.
Yeah.
It's just
It's one of
bauxite.
the most abundant things in the crust of the earth.
However, they couldn't figure out how to make it into like aluminum so that you could, put it on the top of the monument.
Yeah.
They did, but it cost $100,000. And so basically he went to his shed one summer. So he was just a college student, like probably about this age. We could get
A couple
more
of
mustache.
whiskers, yeah.
I don't know if he had any whiskers. He was so young.
Three
And so
hairs
he was
on his
working in the
chest.
shed in the backyard with mason jars for batteries, and figured out how to make aluminum,
Cool.
and became like uber rich.
Uh-huh.
In fact, he formed, I think, the company Alcoa, which makes aluminum like everything.
Yeah.
They're like uber rich, and so he became this super rich kid because he figured out how to do this.
Cool.
So it's called the Hall-Héroult process. Because actually, interestingly enough, simultaneously there was this German dude who figured out how to do it, and they figured out the same thing, and they never talked to each other. So now it's called the Hall-Héroult process.
Kind of like the whole who discovered oxygen thing.
Yeah.
Happened in the same time in different parts of the world. Or calculus, for that matter, yeah.
All right. Anyways, so now we're going to do these problems. These problems, guys, are so easy to do. It is not even funny how easy these are. The key thing is all you got to know is the definition of an amp. That's a coulomb per second. Never think of it as an amp, but as a coulomb per second.
Yep.
And think of a Faraday as a coulomb per mole of electrons. So it's just a big dimensional analysis problem. Now I've got magnesium, and I want to make magnesium metal. So the reaction is Mg2 positive goes to Mg, because magnesium chloride has a charge of +2.
Yep.
And we'll say two electrons here. That's important, that 2 electrons.
Very important.
And you'll just start with the big given now. See, 1,000 grams. I like to start with mass, 1,000 grams of Mg.
Let's convert that to moles.
So what can you convert to? Moles. So I can say there's 24.3 grams of magnesium in 1 mole of magnesium.
Where'd you get that number, Mr. Bergman?
I got that from the periodic table.
Which happens to be rattling around in his head.
I happen to just know that number. I didn't have to actually look at the periodic table because it was in my brain cells.
Yep.
I know that's sad and sick. Okay, the next thing is I have moles of magnesium. And from this reaction, here's my moles of magnesium. I want to convert to moles of electrons. So I can say 1 mole of magnesium is equal to 2 moles of electrons.
Yes.
The moles of magnesium cancel. I now want to convert to
coulombs.
Now we've got that number, 96,485 coulombs per 1 mole of electrons.
Yes.
So I can say 1 mole of electrons is equal to 96,485 coulombs. The moles of electrons cancel.
Nice.
Yeah, like that? Good. All right. Now, this is coulombs per second.
Coulombs per second.
And there's 50 of them.
Mm-hmm.
So I can say 50 C in the bottom, and I can say 1 second. And what it asks for? Time. Bingo. Guess what? The coulombs cancel. I have seconds. So how many seconds is that, Mr. Sanders?
I am punching it into my calculator.
1,000 divided by 24.3 times 2 times 96,485 divide by 50 equals
158,823 seconds.
So 158,823 seconds. Probably in sig fig land. If we said that was 1,004 sig figs, we'd say, you know.
We could do it in minutes.
Yeah.
Divide by 60, 2647 minutes.
2,600?
2,647 minutes. Or 44 hours.
Or 1.84 days.
Or 1.84 days. Thank you, Chris, from the Peanut Gallery.
All right, so not so hard. It's just a big dimensional analysis problem. You get a problem with this in the AP test, and you go, yes, it's so cool. All right, because it's easy.
Oftentimes, though, in the AP test, you'll see one like that in the multiple choice section. You won't even actually have to calculate it. They'll just say, how do you set it up? Or, like, what are the appropriate, like, which of the following is an appropriate way to set it up? And basically, they just want, like, units and stuff like that.
It's all about canceling units. This next problem, example 2, it's going to be solving for mass instead of moles.
So we're going backwards.
Now, it was a chromium 3 to chromium, so I've written my reaction. This is going to be those 3 moles of electrons. So what am I going to start with?
I'm going to start with my time this
time.
time.
Is
Last
good.
time we started with mass and went to time. This time we're going to start with time and go to mass.
So 2 days.
Yep.
I can say 1 day, but I got to convert to seconds because that's the amps are in.
Exactly.
1 day is 24 hours.
Yep.
And then 1 hour is 3,600 seconds.
Yep.
1 hour is 3,600 seconds. Now I've got to seconds.
Okay.
Now, amps are coulombs per
second.
second, and I have my amperage at 7.6.
7.60.
So 7.60 coulombs for 1 second. So my seconds cancel. Now, the way to get rid of coulombs is use a Faraday.
9645.
And that's for every 1 mole of electron. Now, from this balanced equation, I have 3 moles of electrons because of the 3 over here for every 1 mole of chromium. And I need one more thing.
You need the molar mass of chromium. Do you know that
52,
one?
I think, isn't it?
Oh, I'm trying to
1 mole of chromium
52. Man, you're good.
is 52 grams of chromium. Yeah, so I've taught chemistry for way too long, probably.
Only 2 sig figs.
I know them in 52 sig figs. Actually, Mg I knew for 24.3. I knew. Okay,
All right,
what is that?
236.
236. And what units would that be?
Grams.
So 2 days, you get 236 grams of chromium. By the way, that's not very much. Think about this. This is the chromium. Remember that he didn't use chromium 3 positive, but same basic concept. 2 days at 7.6 amps. Can you make money doing that? For only 236 grams?
Yeah.
Probably not.
No.
So that's why he used like 100,000 volts
Yeah.
or 100,000 amps.
Yeah.
It happened a lot faster because if
Oh,
you
yeah.
change this number to 100,000, it's going to do it a lot faster.
Yep.
So he used lots of electricity.
Yep.
All right. Now this one's asking for the actual amperage. So
Mm.
amps are coulombs per second. So we're solving for coulombs per second.
Yes.
So it's the same deal. CR going to CR3 positive. Now this has 8 hours, but that's
Yeah.
already
That's a time in the bottom.
so it's just on the bottom.
We could easily get the moles into coulombs, I think. Let's just start with 0.250 moles of chromium and put that over 8 hours.
Okay, let's do 8 hours. Good call. So we got moles per time unit.
Yeah.
So let's convert our moles of chromium into
Coulombs.
coulombs. So
All
I
right.
can say 1 mole of chromium. Actually, I forgot my 3
You
electrons.
forgot your electrons, yeah.
And actually, I think we're doing it right.
Yeah.
3 moles of electrons.
Would you have done it differently, just for the sake of discussion?
No, I think this
Okay,
is the way. I had
okay.
to think it through.
Oftentimes, guys, the way we do it, there might be other ways. This is just how we do it.
I might have actually just solved for the coulombs and then just divided by the time after the
Oh,
fact.
okay.
That would have worked too.
I like one big problem.
I do too, usually, but I just hadn't thought it through yet because we're looking at these problems for the first time, actually.
Since last year.
Since last year. And then where am I at here? All right, I've got moles of electrons, so I can say 1 mole of electrons is 96,485 coulombs.
Coulombs. Voila, we have a C in the numerator.
So the moles cancel, the moles of electrons and the moles of chromium cancel. Now my hours need to convert to seconds, so I can say
Seconds.
1 hour
Yep.
is
36
3,600 seconds. And that's it, folks. So my amperage is
Divided by 8 divided by 3,600. We got 2.5 amps.
2.5 amps. Not terribly difficult. These problems are easy, folks. Electrolysis problems are just a matter of learning how to play dimensional
Actually,
analysis.
we need 3 significant figures in this problem.
So
2.51
amps. There you go. Okay, one last one, I think. What reaction will take place at the cathode and the anode when each of the following is electrolyzed? Oh, actually, this is an important question.
Very.
All right, so if I have a KF solution, this is about competing reactions. Now, solution means you've also got something else present, and that is water. All right, so if I've got potassium ions, because it's KF,
Yes.
all right, it can go, you can add an electron, and you can turn it into potassium. Now, at this stage, we want to go back to our table. Okay. So if I look up in my table, so if I go to my table here, I need to find the chromium.
Lower
okay?
right corner.
Lower right corner, so lower right corner over here. I need a darker pen, don't I?
Yep.
Black. You see it over here somewhere, Mr. Sams?
Yep, second from the bottom.
Oh, there it is. Negative 2.92 volts. So this is going to be negative 2.92 volts. Got it? The second reaction we have, we can F negative, and that can turn into F2.
Yes.
And that's 2, and then you'll have 2 electrons here. So if we go
Okay.
back to our table,
Yep.
actually I think we're going to have to
Top left corner.
top left corner, and that's going to be,
2.87, but
since we're flipping it,
yes, negative 2.87.
so negative 2.87 volts. But there are 2 other reactions that are key. And folks,
Yeah,
these
there's
reactions
water in there.
are the ones that we're going to have to watch. So if we go back to our table, we need to find the water. There are 2 reactions where water is critical. If I find the water, this is one of them right here.
Yep.
So I'm going to write that one. Mr. Sams is going to read it to me while I
Yes.
do this.
2
2
H2Os plus 2 electrons makes H2 plus 2 hydroxides. And it's negative 0.83.
And then if we go, and we need to find the other water one, and I believe it's
Other-
right here, 1.23 volts. Positive.
Okay, got it?
Got it? So
Yep.
there it is, folks. You see that. Oops, wrong screen. And that's going to be what? A
In
reverse reaction now.
reverse reaction, okay, 2 H2Os
2 waters
becomes O2,
becomes O2
4 H pluses,
plus 4
and
hydrogens
4 electrons.
plus 4 electrons.
So flipping it, it'll be negative 1.23 volts.
So now we've got 4 reactions, and then you can only have one thing oxidize and one thing reduce.
Right.
And so which ones are oxidizing and which ones are reducing? So this one is going, the first one is going down in charge, so this is reduction.
Yes.
Okay, this one is going up in charge, so that's oxidation. This one is, we can think of it, this is gaining electrons, so it's reduction. GR, right? Leo says GR, and this is oxidation. And so essentially we have a competition between the 2 reduction reactions and then the 2 oxidation reactions. Now which one will happen, Mr. Sam?
The one with the big number.
Okay, which would be which one?
For the reduction? Yeah.
Now, it's the bigger number. Now, watch this, because it's the bigger number that, because negative 0.83 is bigger than negative 2.92.
Yeah.
We know that. And so, actually, potassium will not reduce. What will happen is you'll produce
water.
hydrogen
Right.
gas.
Exactly.
So, the winner of this one is that you will produce reduction. You will produce this reaction. Now, if we look at the oxidation ones, let's change colors here. In blue here, we've got two competitions for oxidations, negative 2.87 and negative 1.23. The bigger number is
Negative 1.23.
So the oxidation reaction will be this. So in fact, the potassium and the fluoride will do nothing in this particular reaction. So it says what happens at the anode, what happens at the cathode. Reduction occurs at the cathode. Remember, you keep your consonants together, and oxidation would be your anode. In fact, we just saw this reaction. Did we not?
We did.
This is, in fact, what we had. I put some salt in there. It could have been potassium fluoride. I used sodium chloride, but I got the same reaction. Okay? Now, we go back now to a similar kind of a thing. What about copper chloride? All right. Now, to do this, we're going to use the same. Since it's a solution, we're using the same two water reactions. So I'm going to sort of abbreviate. The reduction of water, the voltages are negative 0.83.
Sorry.
And the oxidation of water, that was negative 1.23 volts. So my other options now are the copper, 2 positive, because it's CuCl2, can go to copper plus 2 electrons. And now the voltage on this one, what's the voltage on this one? When you look at the table, I think
is it
it's
going down to elemental? Sorry.
Yeah, it is elemental. It's 0.34, I think, isn't it? Yep. 0.34.
Yep.
Now, is it negative? Yeah, no, it's positive.
Positive.
So this
Yep,
one,
as
boy,
it
that
is.
blue may not be, it doesn't work very well, does it? Positive 0.34 volts. And this is being
That's reduction.
reduction. Now, we can just look. Reduction, negative 0.83. Reduction, 0.34.
0.34 wins.
0.34 wins. So this is going to be your cathode. My other option will be the chloride can go to chlorine gas plus 2 electrons. I don't know this one off the top of my head.
Chlorine is
Chloride to chlorine?
1.36, but it'll be negative.
Negative 1.36 volts. And so this is oxidation. Negative 1.23 wins.
Mhm.
So the water is going to oxidize, and the zinc is going to reduce. So this will be your
Copper.
anode. Yeah.
You said zinc.
Did I say it back? Oh,
You said
copper.
zinc. It's copper.
Do I smell something burning?
Mr. Meek was doing a demo in the back of the classroom.
Oh, okay. Good. We just didn't want to set the place on fire. That would be very bad. And that was a long podcast, so we apologize.
It was.
And we messed up, but
We
you guys
did.
figured out.
But
so
you probably won't even see us messing up because we're going to edit it all out.
if you know how to do that, that's great, because
Good
I don't
times.
know how.
Oh, yeah. We can check it out.
Okay, so we'll be back at you. Talk to
Yep.
you later. Bye.